give us an intro.
Hey, morning, boys and girls. Today we got a special treat for you. We're going to be touring 24M, a battery company that I'm a little excited about. For those of you who are kind of technical, we're going to talk a little bit about a battery that gives you 660 watts per kilogram. So that'll get your juices going if you're an engineering type. So I'm here today with Miyoki, who's the CEO and president, Richard, who's the CFO, and Tim. Everybody knows Tim. What is your job, Tim?
My title is VP of Global Operations.
Oh, perfect. So can we get a little background? The company, where did the term 24M came from? I don't.
Yeah, 24M, named by our technology founder, Professor Yetomin Chang, right? Uh-huh. So that the 24M means 24 molecular. Okay? So, we started as a flow company, but we changed it to the, more static in the middle. Yeah. But originally, if we try to use the lithium ion for the flow, right? So average, the concentration of the lithium is a 24 molar, molecular. So that's why, we sometimes say, we are the 8 times better than the 3M, okay? That's our target.
Stabbing himself right now. So why don't you tell us a little bit about your background, and then we'll catch everybody else and then we can.
Yeah, so welcome to the 24M today, right? So, my name is Naoki Ota. I've been in lithium ion industry almost 35 years now. 1 year, Sony commercialized lithium ion. I started my career in Japan, but I came to the US 1998, right? To establish the medical, the battery company. This is my, the third startup in the US for the lithium ion. But I joined the 24M as a CTO 2012 originally, but I became the CEO 2019, right? So like I said, 24M is established as a flow company in 2010, right? As a spin-off from the MIT, right? But today you can see, the more than our the semi-solid, we changed the our brand, forever. More than that, we are so excited, to have you into our facility. So, I have two very, sophisticated men, for the tour guide, I let them to speak now.
Hi, pleasure to thanks, Naoki. Rich Chabosky, I'm the Chief Financial Officer and Chief Operating Officer here at 24M. And my background, I was really an engineer by training. Started my career in the solar energy space, co-founded a company we took public a number of years ago. After bouncing around to a couple of companies, including a laser company, I joined Naoki and the team about 8 years ago.
All right, and my name is Tim Rinnick. I'm VP of Global Operations for 24M. I started my career, again, as an engineer, making renewable fuels, drop-in replacements into cars, jets, and other specialty chemicals, and scaled that process out of the lab. And I came here almost 10 years ago exactly, into this same dry room in a process that is long gone, but that we helped to commercialize with Kyocera in Japan. And looking forward to showing you all the technologies we have here today.
Yeah, very cool US made, technology.
Yeah,
we have.
Yep. Yes, and that's another thing I'm very excited about is that everybody always wants to talk about, what's happening in China and China this and China that. This is another example of American ingenuity. Well, at least half of us are foreigners. Yeah, so me and him. But at the end of the day, this is American technology, and I think it surpasses anything I've seen so far. So let's go for a
But I live more than 50% now in the US, okay?
Yeah, but
almost, okay?
Yeah, well,
50.
I started when I was 40. I moved from Canada when I was 40, so I'm only 76 now, so I got 4 more years before.
You hit the 50%.
I'm a little bit more if I calculate.
All right, here we go. So we're going to head to the back of the dry room first, Sandy.
How you doing?
Great. So what we have here is sort of a traditional cylindrical winding operation. And really one of the challenges in the industry has really become people are cutting safety tolerances down so that they can maximize energy density and also reduce costs. And when you do that, slightest mistakes can lead to catastrophic challenges. So what we're going to show you is this is a conventional separator, how it gets wound onto a cylindrical. You can make it well, but if you have a small problem, you can run into an issue. So why don't you go ahead and sort of run through the process.
Sure. We're going to run a four
Yeah,
line.
yeah. And what you can see, Sandy, is look, this is a very short length, but even here, the tolerances, if you make even a small mistake and you run the potential of shorting anode and cathode, right?
Yeah.
So, but go ahead.
Yeah, we probably should mention, because I'm sure somebody's going to say something about it, is that this is a test lab kind of a thing. Normally you'd have all kinds of guides, and it would be
Right.
continuously running.
Right, for sure. So this is, I mean, this whole lab is used for development of the technology. It's not sort of for scale manufacturing. But the key point is that, you know, you're running, this is a short length. So as you go to more sort of standard size cells, which we have over here, you can run into just even a small problem because you're going to get some sort of, you know, movement across and almost look like bamboo. As you can see, if there's a slight problem, you can get some kind of, you know, telescoping.
Yeah.
And that can run into the potential to run into a problem.
Yeah, another one, I think, you know, Tim, you know, you have it, right? Maybe there's some other bamboo one, right? Yeah, so.
You can see how much variation there is just between this one and this one.
Yeah.
See the telescoping?
Yeah. Yeah.
So this, you know, anode and the cathode alignment is very critical, right? So that's why they just try to mimic, as it is. It's very challenging, okay? So you need a lots of know-how and lots of control, right? That's the challenging for the US manufacturing and the European manufacturing because we are not doing that. But what we're trying to do is try to make this much, much simpler by our method. We just want to show, difference, okay? But we use this one for the, development purpose. But we do not intend to get into the mass production with this. Okay? Yeah. Okay.
Cool.
Yeah.
Okay. And so this is a conventional cell that we sort of took apart just to show you kind of what the size of sort of standard cells are today. And why don't you go ahead and sort of unfurl it for us?
Sure. So this is the cathode. This is one of the three components of that jelly roll there, and there are two of those jelly rolls inside of that can.
But anyway, what the key point is that, as you can see, what they've done is they've sort of built a very long electrode. This is the cathode, but then also the separator and the anode are all, sort of aligned very carefully across this entire length, if you would. And this can be 10, 15, 20 meters long, all being sort of aligned properly and perfectly in order to fit inside a can. And the objective of manufacture is still going.
Yeah.
So again, even the smallest error across such a long, it's like when you try to roll up something of such a length, to do it perfectly, to have everything aligned is challenging. But if you can do it perfectly, then you suffer in terms of cost or energy density, right? And so that's the forever challenge that the industry is working on. And if you have slight alignment errors, that's where you can lead to dendrites and other kinds of problems. And so what we're doing here at 24M is we're trying to develop technologies that can obviate the sort of know-how that has been developed by the larger manufacturers over many years of production. And one of those technologies is our Impervio separator.
So it's a jelly roll is this, right? Then they will just open and then the cathode length this, right? So this cathode and the alignment has to be very, very precise, right? This, cathode is always smaller than the inside the anode, right? But as you see, when you're winding, it may shift, right? If you shift, you create a dendrite on the edge, right? So, that may create the internal shock. That's why we need to have the, some insurance, protection, right? That's what we develop, Impervio separator.
So right here. So this is our Impervio separator. So again, it has the conductive layer sandwiched between two insulating polyethylene layers. And this is a traditional Z-stack assembly process. So really what we're showing you is that the Impervio separator, while it has some unique capabilities, it's fully integratable into sort of existing cell designs. Why don't we go ahead and run it, Ben?
Now this is the magic in your battery pack, right?
So so this separator will be, it really accomplishes two key functions. Number one is it will suppress any type of dendrite formation, whether that's a lithium dendrite that will naturally occur from cycling the cell, or whether it's an iron or other form of contaminant that inadvertently got into the cell. So as you cycle a cell, you will typically form dendrites. And so the Impervio layer will keep those dendrites from creating an internal short. Fundamentally, the dendrite won't be able to pierce that Impervio layer. And so that's sort of the key development. The second thing that we can do with it is we can monitor the electrochemistry of the cell from the Impervio layer. The analogy I sometimes use is it's a little bit like having a circuit breaker for your house and a circuit breaker at each individual outlet. So at the house, you can have, the BMS is a little bit like the whole house circuit breaker. It's monitoring the entire system. It's hard to detect with a 200 amp circuit breaker something going wrong at a 10 amp circuit. What Impervio does is it brings that circuit breaker right down to the individual outlet. So if there's a problem in the electrochemistry, we can detect it right there and make the correction right there.
So you have a name for your a type of battery that's different than everybody else's. Why don't you give us a little explanation on that?
Sure. So one of the core technologies that we've developed is what we call Live Forever. Really what it represents is a simpler manufacturing process to make an electrode. So what we do is and we'll show you that in a little bit, but we mix the electrolyte and the active material at the beginning, and then we cast that viscous slurry onto the foil directly. And we don't require the use of a binder. So we cut about half the steps out of the traditional manufacturing process, about half the capital cost. Because the process is simpler, we're able to actually cut some of the operating costs, some of the energy consumption. And then in addition, since we don't have a binder, we can make a thicker electrode. And that has two key advantages. The first is that it simplifies, is that it leverages inactive material. By making a thicker electrode, we use less copper, we use less separator. Secondly, we can achieve higher energy densities. The thicker electrode, because we don't have as much inactive material, we can make higher energy densities. And then finally, since there's no binder, we have a very simple recycling process.
Yes, and this is where you get to the 660 watts per kilogram,
Yes.
which is the most exciting thing for me.
Yeah.
This is fabulous for aircraft and VTOLs and actually cars. Doesn't matter what it is. Lighter is better, and if we can get that kind of situation,
Yeah,
I'm in
because
here all day long.
yeah, once you hit the 400 watt per kilogram zone, like Rich said, removing the metal material
Yes.
is a key for the
Yeah.
watt per kilogram
Yeah, the
improvement.
copper. Yeah.
Yeah, copper, right?
Excellent.
So today we do the large area carpet cell, we call it, but the carpet cell by hand, where we demonstrated the process, and we'll show it to you in a little bit on smaller scale, but the large area carpet cell assembly is done by hand. So what we do is we take the anode and the cathode and we laminate it to a polymer material.
Yeah.
And that is going to form the basis of the sealed electrode that we use to then integrate directly into the pack. So one of our technologies we call electrode to pack, and that is coupling the electrode directly into the pack. So the team here takes the anode and the cathode, they put a separator on it, and then they'll form the sandwich. This process today is manual, but it's very easily automatable, and we're working on that technology as well. So why don't we go ahead and take care of the next step? And so what we have here, Sandy, is we already have the anode down with the separator, and now they're going to apply the cathode on top of that. So they do a simple alignment. So you can see here it's manual, but it's quite simple. Now let me show you, we're on a smaller cell, kind of how we apply the electrolyte, because this is still a dry cell, but down here we'll show you how we apply the electrolyte.
So the one thing most of the people who are viewing this knows I started in machine tools and automation. And in automation, robotics, whatever, the bigger the better. It's easy to do big things. It's tough to do small things, especially if they have very tiny characteristics that separate this from that. And so there's a whole bunch of rules and regulations when you get to small things. Something this large, this should never have a screw up. This is like, this should be a 7 sigma kind of process. So maybe a bad cell in a billion or something like that.
Yeah,
So,
absolutely. Okay, so we'll show you the electrolyte dispense down here. So this tool is a very flexible tool. We use it for a variety of our technologies, including the live forever and the more conventional approaches. But here is where we'll show you the electrolyte dispense. So here the anode is coming in. So this happens to be a lithium metal anode, but you'll see how we do the deposition. They're doing an alignment. They place it. Put the separator on, and now they're depositing the electrolyte onto it. So it's a very simple dispense process. So one of the challenges when you go to bigger and bigger electrodes is getting sort of a uniform penetration of the electrolyte in. So what we've done is we've literally turned that problem 90 degrees, right? So we have a very large area, and then we deposit the electrolyte across the area of the separator. So it only needs to penetrate the thickness of the electrode. And so thereby we can get a very uniform and quick penetration of that electrolyte into it, versus most people, they sort of stack their electrodes or they wind their electrodes and then they fill it, if you would. So we eliminate that challenge from the process.
well, it's big enough and flat enough. So again, I get back to what's the best thing. I want gravity on my side.
Exactly.
I don't want to try and fight gravity.
Yeah, so, but Sandy, we wanted to try it on a smaller scale,
Yeah.
right? So we purchased this system and basically proved it on a smaller format, 300 square centimeter anode. And we actually have it in-house already. It's just a bigger version of this, more nozzles. There's a lot of flexibility in this equipment. We can make discrete dots. We can make channels, continuously flow. We have a lot of flexibility so we can continue to develop the process into high volume manufacturing.
Now we can head back. There's one last step we didn't show, but after we sort of form the large area carpet cell, there's some excess polymer because we've sealed that electrode, right? And there's a little bit of excess polymer. So we have again another simple process where we'll basically use a laser system to eliminate that excess polymer. So yeah, why don't you open it up for us if you could? So we simply place it onto a pallet. Again, as you highlighted, very easily automatable. And then we'll have a laser system go around and cut the excess material off and sort of then have it ready to go directly into the finished pack. Yeah, you might be able to see you can see the laser, just a little red dot moving through. Unfortunately, to protect our eyes, we also limit our ability to film it. So,
Well, at the end of the day, it's not a good idea to have what any industry calls a flash.
yeah.
That's really bad for your eyes, and you got to have a lot of tea bags. That's the only cure. You just boil tea bags and put them on your eyes and try and go to bed.
Just need to give it a couple seconds.
So how much swarf do you get on the, oh, you're going to show us. Okay.
I'm sorry, what?
Swarf, that stuff, the garbage.
Yeah, it's a small percentage. Right now, because we're just doing it manually, all of the tolerances are relaxed, if you would. But we'll be able to cut that down to a small percentage when we scale it. But one of the big advantages, I mean, it's obvious, because of the large area cell, you have a lot more flexibility on tolerances.
Right.
So you don't have to cut everything to 500 micron precision. You can take a little bit more safety tolerance and not suffer from an energy density or cost perspective.
Right.
And then you couple that with our Impervio separators we talked about, and you have a fundamentally safer product.
Well, safe, light, and hopefully it's cost effective. I don't know how much we can get into that, but I assume if it's lighter, it's gonna probably be a little more cost effective. So, and that's what everybody's looking for.
Yeah, we think the combination of our technologies provides higher energy densities, lower cost, and simplified manufacturing, and fundamentally safer, as we discussed.
So let's talk a little bit. We've talked about energy. Let's talk about power. You can do this with any chemistry, I'm told, right?
Correct.
So is this LFP or what do you got?
This cell is
here?
LFP.
LFP.
Yeah, but we
But
could
you could do
use
nic-
NMC, LCO.
Yeah.
We've actually, in this basic design, we've done sodium ion, sodium metal as well.
Really?
So it's, yes, the chemistry is completely agnostic.
Yeah, even the sulfur, cathode too. Sulfur cathode too.
Yeah.
Okay. So any chemistry is a chemistry agnostic. But power is typically electrolyte is key, right? So lithium ion transportation.
Yeah.
So you will see, for the power, improvement in the other section. But you're getting the highest energy density, like we talked, especially the weight, removing the aluminum copper, as much as possible, and also the casing, for the individual cell casing. We try to make the efficient the volume and the weight. Okay? So
Excellent.
because the best battery in the market, you only have the active material, because only the active material is storing the energy, right? So we have to make the active material ratio as high as possible in a limited space. So
Wow, this is cool.
So now we're going to walk over to where we do the live forever, and this is a live forever coupled with a lithium metal anode. So you'll get to see sort of the basic process associated with high energy density. So here, this is our development line. So we do it by hand, but some of our partners and in our other operations, we have a fully automated system that will run this process. But here he's doing the alignment of the individual electrodes. You can see this is now the aluminum side, so this will be the cathode. And it's laminated onto the polymer. And then he's carefully aligning it and then just pushing it together so that when we cast the cathode, we have a continuous casting process. In our tie facility, we have a continuous track of pallets that moves through. But now he's going to cast the cathode, and it will come out this side, with the cathode cast upon the aluminum foil.
So you mentioned Thailand. That's that's your primary manufacturing location, I guess.
So today we do our Live Forever manufacturing in Thailand. We've recently built a facility a little bit outside of the Cambridge area where we are today. It's about 140,000 square foot facility. Our intention is to do the large area carpet cell manufacturing at that facility.
Okay, good. So when do you have that up and running?
So we're finishing the first phase of the construction process. It should be done this summer. And then we'll have the dry room done and we'll be ready to move the initial equipment into it beginning in this summer.
Beginning of this summer. So when do you think you might be in full production?
So that depends on sort of having partners that want to work with us for those materials. But we could be in production by roughly the end of the year.
The end of the year?
Yes.
And what kind of, how many megawatts or gigawatts?
Yeah, so we'll be building it out to be around 200 megawatt hours of capacity. That's the current design. But again, customer requirements, that could scale up or down depending on sort of what was needed.
Okay, so what are you doing here?
So we're taking, after we've cast the individual cells, right, then we are singulating them or slitting them. Now, a normal process, a conventional process, they have to cut through the electrode and the metal. That runs the risk of creating contaminants. But because we have a unique sealed electrode, we only cut the polymer material. We don't actually cut the electrode itself, thereby eliminating the possibility of generating any kind of debris or contamination.
yeah, they only cut to the, we only touch in the polymer.
And then, as we saw before, then the polymers are basically welded together with the laser. Yeah. Or sorry, with the.
They're heat sealed, but then they're sort of the excess material is cut off with the laser. We saw the sort of the electrode formation on the other side of the machine where we basically cast the cathode material and the anode material. Now we're going to show basically the sort of assembly process to form that sealed electrode, which will be the foundation for our electrode to pack technology. And so here what you can see is they're starting to cut the separator material, and in's coming this is the anode, the lithium metal anode coming in.
Eric, I think you may want to look at this one, maybe over here.
And then it'll place the separator on top of the anode. And then it will go to deposit the electrolyte onto the separator, and that will allow it to penetrate in and form the sort of the foundation for the cell. And then on the cathode side, we're going to use our Live Forever cathode, and then we'll join the two and seal it. And you can see that occurring over here.
So are they done coming back?
Oh,
Here's the flip.
and then they're placing the cathode.
Now, one thing we haven't mentioned, but I'm pretty sure, I hope, you've got patents on all this stuff
Yes.
as well, right?
Yeah, so we have over 600 patents in total. Pretty much all of the processes that you're seeing here are highly patented.
600 is a big number.
It is a
What
big
you
number.
about that? And so over here, what we've got is the stacking stage or something?
Yeah, so we just removed the excess material, and then now the individual sealed electrode would then be stacked on, inspected and stacked. And so then you can see it being placed on. So here you can see sort of the stacked.
That's the unit cell that was just made. The unit cell being built.
So now we're going to go show you the recycling process and a little bit of the capabilities of our Eternalite electrolyte. So we had talked in the lab a little bit about one of the key advantages of the Live Forever technology, and one of the reasons we renamed it was because of the efficient recycling. So there's really two elements to it. The first off is because we form this sealed electrode, we can easily separate the anode stream from the cathode stream. That simplifies the whole process, eliminates the whole creation of black mass. And secondly, because we don't have the binder, we have a very simple mechanical removal process. So this is the first part. We just simply mechanically punch out so that we can remove the anode from the cathode side. So this is just a simple punch. But we just want to show from a cell we just manufactured, show you kind of how the whole process works.
Yeah, and that gets rid of the sealing process
Right.
and the laser
Exactly.
welding, basically.
Yeah, exactly.
Melting along.
All right, so
Because
Christian,
you saw that that's a big jelly roll in the lab, right? To separate, anode and the cathode,
Yes.
because even the cathode it's becoming the fragile, right?
Yeah.
It's harder to separate, anode
Yeah.
and the cathode with that configuration, right? With this, unit cell, he's gonna show
Yeah.
how easy to separate, anode and the cathode.
Excellent.
and again, and as you've highlighted, as we make bigger area cells, these processes become simpler in a way.
Well, not only that, you still got a little bit there that you probably will throw away, but at the end of the day, recycling this looks very promising.
Yeah, and since we're doing it by hand today, as I mentioned, the tolerances are much broader than they will be with an automated process.
Yeah, my guess is you're just going to have an automated slitter.
Yeah, exactly.
Yeah.
Yeah. So we're going to show you a little bit about how the recycling process works, but I think we're first going to start with the conventional cathode.
Sure, we
Christian?
can do that, and
Yeah.
then we can do the peeling and
Yeah.
switch to the-
So this will just show you. So with a conventional electrode, right, they have to use a binder to adhere the active material to the foil.
Yeah.
Once you do that, the challenge, even if you can separate, but the challenge of being able to remove those is pretty high. So you need either some hydro processes or pyrometallurgical processes or hydrometallurgical processes. And so this is simply kind of an ultrasonic process. So first we're going to run the conventional cathode through it. And what you'll see is it doesn't really remove any of the material. Then we'll run the Live Forever material through it, and you'll be able to see the difference.
Yeah.
Yep. So running it through basically an IPA ultrasonic bath.
Nothing is
Yeah, so basically the whole process, nothing is removed. And then we'll do it with the, wait one second, Christian, until Sandy. as you can see with the conventional cathode, there was no change. All of the active material stays on it. Yeah, because of the binder. And then what we'll do is we'll peel apart the Live Forever, and then we'll run a Live Forever cathode through it, and you'll see sort of how efficiently the material can be removed and collected. Okay. So this is the sealed electrode that we had just, die cut and punched out. And now he's going to separate the anode and cathode with a very simple process. Puts it on a little vacuum chuck. Simply just to hold it down, and then uses a vacuum, and that's it.
That would be it.
And then there's the separator. And so now you can separate the anode and cathode stream, simplifying the further processes.
That is brilliant.
Now, he's going to put it in that same ultrasonic bath again with sort of isopropyl alcohol.
Yeah.
And you're going to see a bit of a difference this time around. What you can see is where you've actually run we showed it for, you can see where you run the ultrasonic. There's basically bare aluminum. So the active material, the sort of, in this case, LFP, has been removed. And where we didn't run it, you can see that it's still adhered.
Yeah. Right.
So a very simple process to eliminate, or remove, I should say, the active material from the foil. And then what in a sort of production process, in a true recycling process, what this allows you to do is allows you to efficiently recycle the foils, both the aluminum and the copper foil. Of course, the cathode active material is about 40% of the overall cost, so you can efficiently recycle that. But also the graphite materials, or whatever your anode material happens to be made of, typically graphite today, but also allows you to even recycle the electrolyte salts from the process. So we believe we can get up to about 90% recycling or more of the materials of a cell.
And simply, that is very, very simple compared to what everybody else does.
Right. And in many cases, in the current process, right, aluminum, original material cheap, right? So that's if current process, we take the long step, right? They still can do the aluminum recycle, but it's become the more expensive than the the original material. But our case, right? We can simply get the aluminum out, Yeah. So.
And we've demonstrated an LFP recycling process that will, when scaled, be about half the cost of even low-cost LFP material coming out of Asia. So we think we can, as Naoki had mentioned earlier, if you look at a lead-acid battery industry, why is lead-acid batteries relatively inexpensive? It's because they're able to recycle the lead very effectively. Now, sometimes that's done environmentally and from a human health perspective with a lot of challenge, but this process allows for that efficient recycling without the downsides associated with lead, and obviously the higher performance you can get with a lithium-ion cell.
So once you have that slurry, what do you do? Float it like a specific gravity? Is that how you bring out the different?
Essentially, so obviously we would create a large enough mass, if you would, which would be the solvent with the LFP material. Then we run it through a centrifuge, remove out the LFP material. Oh, there it is. And then we can dry it, and then have the core material.
Excellent.
Yeah. Then after the long cycle, right, we lost the lithium in the anode side, right? So after we do the final calcination, we get the lithium back to the LFP, So that's the our the proprietary technology why people develop, and also in this solvent, right? So they have the IPA associated with the electrolyte, right? So we are trying to even extract the lithium from the solvent, right? So because lithium already contained in this solvent, right? So that we are collecting as a lithium hydroxide, from this, so.
Okay, so we've talked a little bit about the Eternalite electrolyte, and one of its key benefits, and Hunter and Jay-Z is his team, are the inventors of this material. So really, it's an entirely new solvent used in the electrolyte that's never been used in the industry before. And it's what enables these unique characteristics. We've talked a little bit about the high ionic conductivity and what that can do for energy density and power, but this we're going to show a little bit of the low temperature side. So what we have is we have basically electrolyte in a freezer at minus 40 degrees C. I guess 41.2 actually. And what we're going to do is show that the Eternalite electrolyte remains liquid at these temperatures and can still has power, and we'll show it through a little radio controlled car. And then we'll show a more conventional electrolyte is frozen and it won't be able to power the car. So let me turn it over to Hunter.
Sure.
Wow.
A quick demo here. So this is what Eternalite looks like at room temperature, which is a liquid. This is a conventional electrolyte, also liquid.
Yeah.
At a room temperature, they look basically the same, transparent and clear. So we put these two wires, same wires, in the freeze overnight at 41 degrees C. This is a controller, so in that temperature, we have one thermocouple and have another thermocouple in there. So just make sure the temperature is actually at 41 minus 40. So I'm gonna open it. Let's do it out. Okay, as you can see, this again is the conventional carbonate electrolyte. It's that
Rock
solid.
Yeah.
Flip it.
Yeah.
Doesn't move anymore.
Yeah.
It's complete. So you can imagine the lithium ion movement is very, very slow
If
inside.
at all.
Yeah, if at all. That's how you lose the range. And this is the Eternalite.
Wow.
Maintains liquid state, so ions still freely to move. So you won't lose too much range or power even at lower temperature.
Well, that's the biggest thing. This year we had a lot of cold weather, and my wife and I both have electric vehicles, and we watched tremendous problems with battery range.
Yeah.
One most important thing you can see here, even if this is at minus 40 degrees C, even if we pull it out, the liquid is still very, very light liquid.
Viscous.
So that
Yeah.
means the conductivity is still very, very high.
Yeah.
Comparing to the all freezing or even
Right.
some kind of low temperature electrolyte.
Yeah.
So that's why you can see even at minus 40 degrees C, it can be still do the power applications. So we want to show you the power application we have here.
That sounds great. Good deal. So is that also in your
Yes.
freezer?
So we will show you next. So this thermocouple is actually attached to the cell we're about to test on the surface. So we know. Yes.
Well, that's why I was trying to stand
So
as close.
this is actually attached to the surface of the cell that we're about to test. So the temperature is not exactly as minus 40, but close enough, minus 38. Most of the electrolyte will just die and be solidified, right? So that's the temperature of the cell. So first cell we're going to test. We're going to test the cell that came with the RC car, which is this cylindrical cell. Right, you buy the cell, they give you this battery, we charge it up, soak it overnight at a minus 41 degrees C. This is actually designed for power cell. So it's supposed to be good at high rate and low temperature. And we'll hook it up and see how it goes.
I'm surprised you got it in
Yes,
there.
yes.
Usually what happens is it freezes up and you get frosted.
Yes. So, yeah, you don't see anything.
So you can see there's nothing happened. So
Yeah.
we plug it in, and then the battery died because it freeze up.
Yeah. nothing happens for this one. So as you can imagine, if you power it by the frozen electrolyte, nothing too
So
much.
just out of curiosity,
Yes.
what would be the temperature that would actually work at? So if you thawed it out, any idea? Would it be like minus, I think minus 20, but
Yes.
what do you?
So I guess on most of the case, on the like this for small tourings, power tours, small
Yeah.
tourings, because they need to save some cost for the concern. So in this case, they don't consider anything about the low temperature at all, because you cannot imagine a tool you can be running in a low temperature. So then in that case, it's only like 0 degrees C is running. But if it's lower than 0, I guess it will freeze. So then for the most electric cars, they only design for the minus 20 degrees C. And then that's why we were extending the range to minus 40 or even lower for these electronic applications.
This is brilliant. Yeah.
So the second one gonna test is the pouch cells. Sorry. I think this is very frozen very well. We took the BMS off for the cylindrical cell so that we have the same power output. And
This cell is about twice or 3 times higher energy density, still keep very high power output because the Eternalite design with the power that can pull out very quickly.
Thank you.
Yeah, so as you pull the other one out.
Okay, there we go.
There we go.
Oh,
Okay,
yeah.
so we got lights and everything. Yeah.
We have
So
lights.
the lights already on.
Okay.
So let's see.
Once you get there.
Maybe it would be too powerful. So let's see.
Holy
You can
crap.
see all the powers.
It's low, what like the normal in the room temperature, and you can see this cell is around 2 to 3 times higher energy than the power tool cell they were doing here, and they can run without any problem from minus 40 degrees C to higher temperature.
Wow.
Yeah. So I think you should maintain most of the powers in this case, and it's soak all overnight at minus 40. So you
Yeah.
buy a toy Alaska, for example, and let it sit outside. Next day morning, you can still run it.
So in this case, if we apply these cells, this is one of the simulations we're doing right now is, you can see this is a car, right? So
Yeah.
although it's a toy car, but when it is a real car, you can expect the same performance or almost similar range at a low temperature as well.
Oh, this is a big step up. Yeah, huge. Okay, well, gentlemen, you gave me a tour. I got to tell you, you've surprised me at least 3 or 4 times. I can't believe the recycling thing was really a big deal, because I've seen plenty of recycling being done, and I never saw anything quite like that. I'm impressed with the size of these cells. They're just astronomical, and I like the idea because I'd rather have that than this. If I'm in manufacturing, that makes a lot more sense to me for assembling a battery module. So I'm really happy about that. You surprised me on how you get to 660 watts per kilo. I'm impressed with that. Everything about this seems like I don't know, one little invention after another, and they're not little. These are all pretty dramatic inventions. So I've got to ask, what's your next step? I mean, you got 2 hats here, CEO or COO and CFO. Where's the money, boss?
Yes.
By the way, he told me to ask that question.
I believe that actually. Well, look, right now we've got capital, but we're in the process of raising additional capital to fund the commercialization of these technologies. Really, Naoki, the team, have created what we believe is a really unique and outstanding strategy. It starts with the ability to solve some of the fundamental problems in the industry. And we believe we've taken those through sort of the development and demonstration and validation phase, and now we're ready to move into commercial scale. So we're working with a number of partners of ours to try to raise the capital to bring that into full commercial production. But that's a process that's ongoing as we speak.
Yeah.
Wow.
We focus on the bottleneck, the issue in the industry, right? We believe the safety and the cost and low temperature charge and rapid charge and recycle so on, right? That's the bottleneck, right? But initially, rather than we try to jump in the production, the US have the very good brain power, innovation, right? We the secure those new technology, right? And the protecting, right? So for the production, we are trying to work with the large company, for the partnering, right? That's why here is the patent, you can do the production. We cannot do it, right? So that's why we they develop and we prove manufacturing stage. Then they're working with the large manufacturer, particularly end user like for the GM, those company is good to us, right? So the good thing that we have the very strong patent, more than 600 patent, protection. Right? The next step, we are trying to get into the volume production, in the US, some level by ourselves. And with our partner, like this.
Yeah. Well, a couple of, we have one major OEM that we work with and 2 or 3 others that are kind of tiptoeing around. But I can guarantee you that I'm going to be alerting them before this video goes out. The other one is the Department of Defense, especially the Navy. The Navy and the Air Force or whoever wants to have VTOLs, this is kind of what they need. And so I'm going to try and work my tail off to get them to come and contact you, because quite frankly, this is what we need in order to, in order to, everybody says, I don't know why, but they all keep saying, well, we have to catch up to the Chinese. You can't catch up to the Chinese. The Chinese are at the 50-yard line, you're at the 0 line, and it's a 100-yard dash, okay? If they're already here, you have to have something that goes boom, like that. You have to leapfrog them. This is kind of a leapfrog technology, and we've seen a couple of them, but for some reason or other, I can't get people to wake up and reach for their wallet. So I'm going to do my best to.
Yeah, thank you. I agree. I always say, right, US, right, we want to play our form game and our, strong sport, right? For instance, China is very strong in the ping pong, right? If we try to, the challenge back in the ping pong in the US, it's hard, right? But we have to play the tennis instead of the ping pong, right?
Yeah.
We have to change the game, to be more, effective in the market.
Yeah.
That's all we are trying to do is, changing the game, right? With our own way. Basically, we don't want to be in the same line. We need some jump,
Yes.
to change, right?
And that's what I'm looking at here is a leapfrog. You're jumping from where everybody else is to where I haven't seen anybody go. And I've been to lots of battery plants here in well, not so many in the US, but definitely in China, and Korea, and actually in Japan too. But I haven't seen anything like this. So I'm very, very, very excited. I don't know if we mentioned it, but this is about 1 meter by 1/2 meter, which is precise. Actually, I gave a speech a while ago, and he said, what would be the optimal size cell? And I said, about 1 meter by 1/2 meter, and here you are. The whole audience started laughing when I said that. There'll be a couple of sad faces if they see this, that's for sure. But this is where I think everybody needs to be, and I'm just totally amazed, really am. This is really, really good stuff.
I think you and Naoki think very similar. Like Naoki really pushed us as a company to do something of this sort of scale. He's been in the industry for 35 years, one of the world's experts in the industry, and he really saw what the challenges of the conventional technologies are. And that's why we developed that suite of technologies, including sort of the simplified process and the scale that you can get with this electrode to pack technology. And then the combination of a fundamentally safer design with the Impervio separator.
Why don't we hold this up here so that everybody can see what's going on?
Right.
So give an explanation.
So the conventional separator, what it is just a passive material. It's a polyethylene layer, typically very thin, and that's what keeps the positive and negative apart, and that's what keeps safe operation. But as you cycle a battery, you run the risk of creating some form of dendrite or other ways of creating an internal short. And what we've developed and what Naoki and the team have developed is really a capability to eliminate that as a source of failure. So the first thing we do is we put a conductive layer into the middle of the separator. So we have on each side of the conductive layer the polyethylene material, and that sandwiched material is conductive. And then with that, we're able to suppress any form of dendrite. So we are able to sort of supply the electron that the dendrite is seeking from that middle layer, and then avoiding any potential short. And then secondly, we can monitor that layer. And if we see a change in that, then we can instruct the BMS to discharge that cell in a safe manner. And so you have a fundamentally safe cell. And, you know, there's been a number of recalls, as you're aware, Sandy, very large dollar values. But the percentage of product that was actually defective was very, very small.
Minor,
But it was impossible to discern which were the good versus the bad. With the Impervio separator, because we're monitoring at the electrode level, we know which cells are good and which cells are bad. So mass recalls can be a thing of the past. You can simply replace the defective cell and not touch all the cells that are operating properly.
So that was when we were down on the floor and walking around, I said, oh, you have a barcode on each one of the cells. So that must relate back somehow to the battery control module?
Absolutely. So we have a MES system that tracks all of that information, and obviously our scale partners can do that as well. And what that allows you to do is, if there is some form of a defect, then you know precisely which product is at risk. And then then you can sort of target sort of your actions to the batches or to the product that is at risk. Conventional approach, you can't do that. You lose track of it.
No.
But with this approach, you know exactly what.
And if you need it, the lot information is in the BMS zone, right? That we know which one, identify, that we can test, health of the battery, remotely, right? So basically, this one have the one more information, like Rich said, from the each of the electrode, right? So, rather than the control, the entire pack, right? We have the individual electrode control, like he used, individual electric outlet. We have the fuse, under the, detection system. And I understand, the some debate or electric vehicle has the less, the fire comparing to the combustion engine, right?
Yeah.
That's why we are not saying industry is not doing great, but always you want to have the improvement, like, we integrate the airbag system in the car, right, to protect the more people. We are more than happy, they don't use, the Impervio forever, but if you have those protection, you can always protect, the 0.1%, close to the eternally zero, right? That's the target,
That's it used to be the 6 sigma process, but now it's 7.
Right.
7 sigma is what everybody's shooting for now, especially when you get to batteries. And it's achievable. It doesn't have as many variables as like an engine.
Right.
And it's funny that you mentioned the engines, ICE vehicles catch on fire more than electric cars. You'd never know that if you talk to any kind of one of these newspaper kind of people. They just don't look at data. They just look at this purely emotion. But at the end of the day, if you take the you know, if you take the year whenever 2016 or something, or 18, I can't remember what the number is, and you go from there to now, and you compare it directly to the same amount, and you know, do a qualifying, it comes out that it's like 3 times more likely or 4 times more likely to get a car fire with an ICE engine than but you don't see that because, you know, I don't know. I don't know much about selling newspapers, but I do know that that's their business. Selling newspapers is the business, not telling the truth or whatever.
But as a battery engineer, right, you know, as you know, have the more cycle or longer, you know, the life battery, right, you know, it's, you know, tend to create the more dendrite, right?
Yeah.
That's why, you know, maybe the car life, you know, 5 years, 8 years, but some people may drive 15 years, you know, 20 years.
Yeah.
As you put the longer period, you know, those risks, you know, will go up, you know, without the protection, right? So that's for making sure, right? You know, how many people drive 15 years, you know, 20 years for EV, we don't know, right? But, you know, no matter what, you know, if we want to protect, you know, those issues, you know, that'll be better.
Well, I don't know about years, but I do know about miles, and there are people in California that are running. They have about 1 million miles going between LA and Vegas. It's a car service test loop, and they don't seem to have problems. The rest of the body, the suspension wears out and brakes and stuff like that. But the actual driving back and forth, do they, you know, rocket ship fast anymore? No, they're just an average car now. So when it comes down to it, this is the right way to go, regardless of what anybody says. You know, even the president, I think he's going to change his mind after a while. But at the end of the day, this is the wave of the future, electric vehicles, and this is the wave of. This is the way we get there. I mean, this is an ultra safe battery. It gives that's more than a third more watts to kilogram than I've ever heard of before. All this tells me. So let's get to the last one. If the numbers in my head come out close, I don't know what you'd find in volume, but is this going to be a less expensive battery than you know, per kilowatt hour?
Yeah, that's correct, right? You know, we call the electrode to pack, you know, the technology, right? You know,
yes. So
you know, you know, we are putting the many of this layer into just the one packaging. So image is, you know, only the 6, you know, pack, you know, inside the EV, right? Instead of the 300 can, right? Inside the, you know, if that's a small cylindrical you are using, you know, couple of thousand, right? So, you know, we reduce the bunch of the, you know, can and the bus bar, right? Yeah. That's also the, you know, contribute to, you know, energy density, you know, improvement. You know, we try to make the, you know, high safety, you know, the high energy battery, right? It's typically, you know, opposite, and also the achieving the low cost as well.
Yeah. I mean, so we've done a numerous analysis. Obviously, we have one of our partners is in scale production, and so we have a sense of what the cost structure is. But we also have worked with some outside firms who've come in and analyzed it. And their analysis is that the combination of our technologies not only improves the energy density and adds to the safety, but will also lower costs by about 30% over conventional approaches. Well,
30% is a big-ass number.
Yeah.
There's no question about that, and quite frankly, that's what we're looking for. At 30%, that puts it well under the $100 number that everybody's been trying to use. So I'm pretty impressed. 30%. That just took my breath away. I lost my whole train of thought. I was thinking, you know, 15 or something, but if it's 30%.
Yeah, I think with the conventional, maybe the 15%, with the same, you know,
Yeah.
forever is 30%.
Right,
We
when you
just
add-
want to make sure.
Exactly. So the electrode to pack by itself is about half of that improvement, and then the live forever electrode adds the other. So both are roughly 15% each. So when you combine the two, that's how you get to the 30%.
You're just trying to make me feel better. I'm on the verge of having a stroke, and you don't want to take my cold dead body out of here. But this is kind of like amazing. That totally blew me away. Holy moly! So I definitely have to start making phone calls when I get back to my customers, anyways, to see what's going. But really and truly, I've got two reasons for being here. One was the automotive industry. The other one is the defense, and we're working on a new ship, the DDG-X, which is a new destroyer, and it's in the news and stuff like that. You can read about it. I don't want to talk too much, but at the end of the day, we need a lot of power, a lot of batteries, and I need ones that are not going to have a problem if they get hit with shrapnel and things like that. And we talked about dendrils. So let me ask the big question here. What happens if I stab this with a knife or shoot it with a gun?
Yeah, so with the Impervio, the first, we can detect, something's wrong happen, right?
Yeah.
So at least, as soon as we got the signal, right? We try to, find out, another route to discharge, right? So we integrate that. That's why the bullet point, the current, doesn't flow much, right?
Yeah.
So depend on the the bullet size and so on, but we protect it. People can we detect it. The people can take another action.
Yeah, I think as Naoki said, there's a lot of built-in safety to the designs that we've put together. So even in just normal operation, forgetting about the bullet and the knife, the fact that we seal the electrode, we actually seal the separator to the polymer. That prevents the electrode from shrinking or prevents any type of issues around the edge, which sometimes happens in sort of a conventional manufacturing process. And then you couple that with the Impervio separators Naoki just mentioned. Now if there's some sort of piercing, whether it's from an internal process like a dendrite or an external process such as a bullet or knife, we have the ability to detect that and then discharge the energy of the battery outside of the battery. Once the energy is depleted, then the risk associated with the short goes away. And so we have that sort of double capability because of the technology Naoki and the team have developed.
Well, the only, General Motors didn't have a problem with LG, but they had a problem with folding. Yeah. And when you're at this size, remember I told you on the floor, I'm a big fan of big when I'm trying to automate things, and the reason for that is because big is easier to control. Small, when you go into these machines move at wicked fast speeds. I mean, it's a blur. You can't really, your eye can detect things at 1/10 of a second, and this goes faster than that when you're making them. So, and that's where things went wrong. Just a little corner deformation, and now the anode and cathode kind of kiss, and this is not a good, it's a kiss of death. So that's kind of like what happened with LG, and I'm sorry that General Motors suffered under that, but at the end of the day, everybody remembers Chevrolet. Nobody knows who LG is unless it's a refrigerator. So these are the kinds of things that you've got to try and ensure you'll never have a problem with. With this, I didn't get a chance to actually feel the thicknesses, but I'm assuming that the thing is the cathode is thicker than the anode, right? Is that it, or is it the other way around?
anode is bigger than the,
Yeah.
the cathode, and the anode is thinner than the typically, anode is thicker than the cathode.
Oh, sorry, got it reversed. Yeah.
yeah.
So with yours is so thin. I don't see how that could even happen with that.
Yeah.
And it's sealed all the way around.
Right. So important one, right? Cathode and anode shouldn't touch, right?
Yes,
Last line of the defense is a separator, right? Separator always has to insulate electrically, right?
Yeah.
So issue is if we open there, right? There may be some the moving, right? Especially the people doing the winding stacking, they do the very precise alignment, but when you move, it may move, only the couple. That they sometimes create, or when they put in a case, right? They may squeeze on the edge, right?
Yeah.
Then you may, the touching cathode and anode, right? But our case, like Rich said, separator already sealed, the issue, the direct touch, is by design,
Right.
we eliminate, we do the DFME and so on. By design, we protect it, right? It's not process, right? It's the design, right? Second one, right? If we have in the worst case, those, bent it so on, very badly, so on, right? Then, it's not direct short, but it may create a dendrite. Dendrite. But a dendrite, we protect by the, Impervio, right? At least we can detect, we remove it. So, for those, the failure mode, we have the all protection by design, not by process.
Yeah, and processing, to have a 7 sigma kind of process, it has to be designed in. You can't process in quality, it doesn't work.
Right.
You only think, you can make certain things work through process, but it's better if it's designed so you never have to worry about it. And quite frankly, I was watching how everything was going there. This is going to be probably manufactured like soup cans, where you're going to be blowing, like in soup cans, you throw the lids and basically all the cans get blown around. I mean, this would be an ideal application for no touch, and that's kind of like another way that you can even go faster. If you just use, I usually say air is only good for breathing when I talk about machines and whatnot, but when you have something like this, this could be like a leaf blower kind of automation. And I've done those in the past. If it has to be really ultra fast, you can't beat air hockey tables. Yeah. There's so many things here that we've seen. It's kind of like overwhelming. I got to tell you, I'm very impressed, and I'm even more impressed. I wasn't expecting to see this. I did read up, and a lot of people send us stuff, and I mean, everybody's talked about different things where I've seen it and I didn't like it, and I told the owners of the company that they were lying to me and stuff like that. I can't say here for a second that I'm anything but super duper impressed. This has been a good day for me. When you get old, a long time from now for you. But anyways, when you get old, time becomes much, much more precious. I hate wasting my time talking to a moron. But this was really stunning. Is there anything else that you wanted to add to this, or, I mean, because information overload has occurred at my
only
house.
the thing, minus 40,
Well, the minus 40 thing, oh my God, how did I forget that? Yeah. I'm telling you what, my wife and I were complaining bitterly. My Cybertruck, I'd lose 30% in a trip because it was really cold this year. I mean, and my truck just sits outside. Sue's Model 3 sits inside the house. I was losing at least 30%. She was losing at least 20%. With your chemistry, and I'm looking at the whole chemistry, not just at minus 40, I'll take that all day long. Yeah, I can tell you right now, everything north of the Mason-Dixon line is going to kiss you on all four cheeks if you can get this stuff out, and that's a fact. Yeah, yeah. So I don't know how I missed that one or forgot that one, but that also. I mean, everything I've seen today has been a big surprise. Or let me rephrase that: a proven surprise. I get a lot of surprises. Some of them aren't so good, but this has been brilliant. I really mean it. Anything else that I goofed up on?
I think, thank you very much,
Yeah, wow.
So we keep on working very hard, let this happen, one by one.
Well, I'd like to see this get into production in a hurry. So if you got tons of money out there, maybe you can contact these guys. And I will talk to the guys at the Department of Defense. But I don't know what's been cut and what hasn't. This has been brilliant. Thank you.
All right.
Thank you so much.
Sandy, really appreciate it.
Sandy,
Yes,
appreciate
thank you.
it.
Thank you so much. This
Thank
was
you.
really good. Thanks for watching, everybody. I'm not often lost for words, but this has been a really good trip. And I hope you enjoyed it as much as I did. Thanks.